বিসমিল্লাহির রহমানির রহিম। শিক্ষার্থীরা তোমরা আশা করি সবাই ভালো আছো। C417 এর বিম ডিজাইন এর অংশে তোমাদেরকে স্বাগতম। আজকের ক্লাসে আমরা নন কমপ্লেক্স সেকশন এর বিম ডিজাইন অংশটা করব। গত ক্লাসে আমরা কমপ্লেক্স সেকশনের ল্যাটারাল টরশন বাকলিং নিয়ে আলোচনা করেছি এবং কোএফিসিয়েন্ট ফর নন ইউনিফর্ম বেন্ডিং মোমেন্ট সিবি এর ভ্যালু নিয়ে আমরা আলোচনা করেছি এবং কিছু অ্যাসাইনমেন্ট দিয়েছি। আজকের ক্লাসে আমরা যদি নন কমপ্লেক্স সেকশন নিয়ে আলোচনা করি, তো আমাদের যে নন কমপ্লেক্স সেকশনটা থাকে এআইএসসি তে বা আমাদের যে স্ট্যান্ডার্ড সেকশন অ্যাভেলেবল সেকশন গুলো আছে, এগুলোতে আমাদের নন কমপ্লেক্স সেকশন স্ট্যান্ডার্ড আমাদের ডব্লিউ এম এস এবং সি যে শেপগুলো আছে, এগুলোর মধ্যে প্রায় সবগুলোরই আমাদের ওয়েবগুলো হচ্ছে কমপ্লেক্স। তো আমাদের ওয়েব নিয়ে আমাদের নন কমপ্লেক্স কোনো অপশন নাই। এমনকি ফ্লেঞ্জের মাঝেও আমাদের অলমোস্ট সকল ক্ষেত্রে কি কমপ্লেক্স সেকশন, তবে ফ্লেঞ্জে কিছু কিছু নন কমপ্লেক্স সেকশন আছে বাট স্ল্যান্ডার সেকশন নেই। অর্থাৎ ফ্লেঞ্জে ল্যামডার ভ্যালু অর্থাৎ ফ্লেঞ্জে ল্যামডার ভ্যালু কখনোই কি 1√e/f ক্রস করবে না। অলমোস্ট সকল ক্ষেত্রে ফ্লেঞ্জের এই ল্যামডার ভ্যালু এই ইকুয়েশন দিয়ে bf/2f দিয়ে যে ল্যামডার ভ্যালু পাবো, অলমোস্ট সকল ক্ষেত্রে কি ল্যামডা কি এর সমান ছোট। কিছু কিছু ক্ষেত্রে আমাদের এই ল্যামডার ভ্যালুটা হচ্ছে ল্যামডা পি এবং ল্যামডা আর এর মাঝে থাকলে তখন হচ্ছে আমাদের নন কমপ্লেক্স সেকশন। স্ল্যান্ডার দ্যাট ইজ ল্যামডা কখনোই কি ল্যামডা আর এর বেশি হবে না for available the section standard sections, and it can be possible that lambda will be greater than lambda, that is slender section, and web may also be non-compact or slender, but this case this is not true for standard available sections. But if we make built-up sections, and then it is possible, and this is generally discussed as a plate girder, which is out of our scope. So if the section is non-compact due to flange non-compact, then the nominal moment capacity will be governed by this equation, that is Mn equal Mp, that is plastic moment minus 0.7 Fy Sx, and that is lambda minus lambda p by lambda r minus lambda p, lambda rp, and lambda r is also stated here. So, and the unknown value is Fy, this is the strength of steel, which will be given or known. Sx is section modulus about x-axis, which we will get from section properties Mp, that is Fy Zx. This will be also be known from section properties. So using this equation we can find the nominal moment for non-complex sections. But the fact is, if the beam is also unstable due to lateral torsion buckling, then what will be nominal moment? In such cases where the beam is non-compact, we have to calculate two nominal moment. One is for non-compact sections, that is flange, non-compact part, and another is for lateral torsion buckling. So we will get two moments, and the minimum of this will govern the capacity. So we will go directly to a problem, and in this problem we will also revise the lateral torsional buckling problem and the full go through of non-complete section. So this is from example 5.6 from book of Sagui, Design of the Steel Structures. The question is, a simply supported beam with a span of 45 feet is laterally supported at its ends and subject to the following services. Dead load 400 pound per feet, which includes the self-weight, live load 1000 pound per feet, yield strength 50 KSI, and the section is W 14 into 90. You have to find whether the section is adequate for this live load and dead load or not. So আমাদের লোডিং কন্ডিশন দেয়া আছে লাইভ লোড এবং ডেড লোডের কারণে এবং ম্যাটেরিয়াল স্ট্রেংথ এবং সেকশন প্রপার্টিজ দ্যাট ইজ W40 into 96 দেয়া আছে আমাদের we have to find whether this section is adequate or not adequate. So please keep in mind that we will be provided with the section properties chart which I have shown, which our mining staff have already given to you. But when this kind of problem is given to you, that find the section is adequate or not adequate, or find the moment capacity of this section, then there some properties will be withdrawn from the chart. Some value of some or some magnitude of some functions will be withdrawn from chart, which you will have to calculate by your own judgment. But when there is a problem of finding a suitable section for such kind of loading, that is a design problem, all the section properties will be given. So we are given with a W14 into 90 section. So the section properties from the chart is we have seen this chart, which will be ASC table for section properties, and there you can find the W14 into 90 section. The depth is 14 inch. We also know that if the section is 14 into 90, then the depth will also be 14, around 14. Depth is given as 14 inch. Thickness of the wave is 0.440. So we are given with TW, depth, and PF, that is flange width, is given as 14.5, and thickness of the flange is 0.710. And there's also some properties, that is about x-axis, I, S, R, and Z are also given, and same for x about axis Y, that is I, X, R, and J is given. RTS and H not are not given here. J is also given, that is 4.06, that is torsional constant, and CW, the working constant, is 16,000 inch or 6 level. So we find that is A, we can calculate A, that is from section properties. If we see this here, we are given that the flange width is 14.52, that is 14.5. The flange thickness is 0.710, the wave thickness is 0.44, the overall depth is 14 inch. So we can also easily find the area of the section, that is 0.77 into 14.52. This is in 2, that is 2 into 0.71 into 14.52 plus the wave area, that is 14 minus 2 into 0.71 multiplied by 0.44, and the IX, SX, and RX, IY, SY, and this is also given. So we have to find firstly whether the section is compact or non-compact. As we know that lambda equals Bf by 2Tf. So this value 14.52 by 2 into 0.71 is 10.225, and we know that the highest limit of plastic flange is 9.1516. This comes from 0.3 root over E by Fy. E is 29,000 KSI, Fy is 50 KSI given. So the section is not compact. Then we have to find whether the section is non-compact or slender. So that lambda r equal 1 root over E by F, that is 24.08 as the section, and for lambda is 10.225, which is within lambda to lambda p. So the shape is non-compact, and now we have to find for finding nominal moment capacity based on non-compact section, we have to find MP, that is MP will be Fy into Zx. As Zx is not given here, we have to find the value. So to find the value of Zx, which is in our view, our section is like that, 14.52 by 14 inch, that is the width is 0.44 inch, and the inch is 0.71 inch. If we cut the section into two parts, then the half part is shown in the right figure, right? And in this figure, we have to. This is, we can call this as a compression part, and the CG of this compression part we have to find to get the value of A. So if we want to get this value with reference to this neutral axis, so we have to find the CG of this portion with respect to neutral axis. So this value is, we can find, and this value as A is this momentum is the distance between resultant of compression and tension part. So this is A. So the value from neutral axis will be A by 2. So we can write A by 2 equal, that is 14.52 into 0.71, that is area. We can say it A1. So A1, then we have to find Y1. As the total depth is 14 inches, so we are thinking about 7 inches. So Y1 will be 7 minus 0.71 by 2, that is the CG of this point. It is located at 0.71 by 2 inch from the top. It is located at 0.71 by 2 below the top flange. So, but we can write this as the web portion in the middle half is 6.29, so we can write 6.29 plus 0.71 by 2. Anyone we can write. So the value of A by 2, and so this is the area. The first area is 14 into 52 into 0.71 plus 6.91 plus 0.71 by 2 plus the A2 portion is 0.41 multiplied by 0.62, 6.29 multiplied, that is A2, and Y2 will be 6.29 by 2. So Y2, and we divide this by A1 plus A2, A1 plus A2, then we can find A by 2 is 5.904, that is A equal 5.904 into 2, and if we calculate the area, then we can find this 2 flange and web. So the area of each part individually, and that is 26.1536, and Zx, that is ZX, you will. So now we get plastic section modulus ZX equal I by 2 multiplied by m momentum, and this is the area of tension or compression, and this results as 155. The unit is inch cube because it's a unit of area is inches square and the momentum is inch, so it's inch cube. So we can now calculate the plastic moment MP, that is Fy into Zx. So we know Fy is given as 50 ks and Zx is 155 or 157, that is 7850 gives inch. So now we have to calculate the nominal flexural strength based on flange local buckling. So this flange is non-complex section, and for this the equation is MP minus MP minus 0.7 Fy Sx lambda minus lambda p lambda r minus lambda p. We have already calculated MP as 7850 and Fy is given as 50 ksi and Sx is obtained from the section properties is 143, and the value of flange portion, that is lambda p, we have already calculated here. Lambda is 10.225, lambda p is 9.1516, and lambda r equal 24.08. Putting all these values, we get the nominal flexural strength is 7646 gives inch, which is less than MP. So it is the nominal moment capacity of the beam based on flange local buckling. But we are also to check the lateral torsion buckling, and we have unsupported length of 45 feet as stated in the question. This is because if the beam is supported of 45 feet and there is lateral supports in the support sections, lateral supports in the support sections only. So LB is given as 45 feet. Now we have to calculate LP. So LP will be, as per equation, 1.76 ROI root over E by Fy. All this data will be from section properties. ROI, radius of gyration about Y axis, also given as 3.7. If we go to the section properties, we can find this is also given. And E is 29,000 ksi as steel and Fy. Based on this, then LP is 13.07, so it is not in the range of no instability, as our LB is 45 feet far greater from this. Now we are to calculate LR. To calculate LR, we need the value of RTS, H naught, and other values. So now we will calculate LR. So we need RTS. So RTS, we will calculate RTS. This value is known: 29,000 ksi, 50 ksi, J is given, and C for W symmetric I section is 1. J is given as so J is given as 4.06 from section properties. Sx equal 143, there is also given, and S naught we have to calculate the distance between the centers of flange, and The space is also known, so we have to calculate RTS and H naught. So before it we have to calculate, and we know RTS is square equal root over IY CW by SX, and IY is given as moment of inertia about y-axis is 362, and CW is given from the section property 60,000 is 6, and SX 143 from this RTS equal to 4.102. So H and the H naught, the distance between range of the sections, sandpit between the sand planes, and we know the total height is 14 inches, and this sandpit of the planes will be 0.71 by 2 inches from the top, and the sandpit from of this bottom end will be bottom 0.71 by 2 from the bottom. So ultimately the distance between the planes will be 14 minus 0.71 by 2 minus 0.71 by 2, that is 14 minus 0.72, that is 13.29 inch. So from there we can put a values of RTS and H naught. So 1.95 RTS we have already calculated 4.102, E equal to 29,000 KSI, as 0.7 Fy equal 50 KSI, J equal 4.06 from the section property, C equal 1, Sx H naught equal to 13.29 we have calculated here, and other values will be same. JC Sx is not the same term or square, and 6.76.7 Fy by Uy. Then this results as 5,000. Sorry, this results LR equal 510.47 inch, that is 42.53 feet. So the slender's limit, lower limit of the slender lateral torsion buckling is 42.53, but we have LV equal 45 feet. So our will be in the third range. As far we can remember, the range was such that, so it's no instability condition, inelastic lateral torsion buckling, and this is the elastic lateral torsion buckling for LB equal LB greater than LR. So we'll be in this range, and in this range MN equal FCR into Sx. So we have to calculate FCR value, and we know this FCR equal CB pi square E by LPRT square plus root over 1 by root over 1 plus 0.07 JC as not LB by RT square. In this equation all the terms are known to us, and we are little bit confused about CB. And from the loading condition, as it is subjected to uniform load, both dead load and live load. So for uniform load already we have calculated CB equal to 1.14, and so based on these values we have value, so we can calculate CB equal 37.2 KSI, FCR equal to CB equal to 1.14, then pi square E LB we have calculated 45, given 45 feet span, and then we are converting it in inch, as all the units are in keep inch. So based on this value, FCR results as 37.2 KSI. Now we have to calculate nominal stern, that is MN equal to FCR SX, and from this value we find FCR equal to 37.2 KSI and Sx is 143. Then the nominal moment is 5,320 keep inch, which is less than MP equal to 7,850, and if we convert this into keep rate by dividing it by 12, then it is 443.33 keep feet. So we obtain two values. One is based on lateral torsion buckling, is 443.33 keep feet, and based on flange local buckling the value is 637.5 keep feet. So we have to take the minimum of these two strengths, nominal moment strength. So our 637.5 and 443.33, so the lowest is 443.33. so the nominal moment capacity of the beam is 443.33 keep feet. So we have to calculate based on LRFD method and also SD method. In LRFD method, we have to multiply the dead load by 1.2 and live load by 1.6. So we are multiplying dead load by 1.2, that is 400 into 1.2, and 1.6 into live load, that is 1000. Then the loads becomes 2080 pound per feet, that is 2.08 kip per feet. We have to convert it into moment. The ultimate moment M is W square weight, because it is a simple supported beam with W load per unit. So the maximum moment will be W square by 8. Highest point will be W square by 8. So it's 527 kip feet. And we have the nominal capacity as 443.33, and the design strength will be 90% of this, that is 399 kip feet, and we need for ultimate moment is 527 kip feet. So the section is not adequate. It is LRFD method. In SD method, we don't need to multiply the loads, but we will limit the allowable moment by dividing Mn by 1.67, that is the nominal capacity is 266 kip per feet. So the allowable moment capacity is 266 kip per feet, and actual loading condition, the moment total load is 1.4 pound kip per feet. The ultimate moment, so the actual moment is 355 kip feet, but we have allowable moment is 266 kip per feet. So the beam section is not adequate.